why don't we think a little bit more about what other tests we could do? Let me see if we could formulate how we can actually ask real questions about our data set beyond some of these mathematics. In our next question, we're going to ask, how do we go fishing for significance? And in this question, I want to share with you some common statistical questions, some common things we can ask about the real world, about our actual problems, things that we can prove or at least accept or reject, and how we formulate those in terms of the mathematics. Because I'll be honest with you, one thing that frustrated me so much when I was learning statistics was there's a lot of math, but I really just want to know how I can show something that I can take to the bank, something that I can prove about the real world, not just about some mathematical entities. And so, what we're going to do is we're going to try and ask questions of the form, did something that I changed have an effect? Did something really happen? Was it real or was it noise? When I sampled something and it gave me some value, is that a real value or is that just a noise as a consequence of the sampling? If two things occurred, were they equally likely or not? These are the kinds of questions I might ask. But let me be more specific, and we'll go back to our data set and we'll see what kind of questions we are capable of asking. Here, I have some before and some after. I have a before population and an after population. And I can show you what really happened in the data by just peeking at the population. In general, I don't really have the ability to peek at the population, or if I did, probably I wouldn't care about these statistical tests. I could just look at the population and have it answer for me. But if you look at the population, something happened. The mean value before was 75, the mean value after was 69. If these are temperature values, what that means is I invented a new type of water cooling, and it reduced the mean temperature down to 70 degrees. This was successful. I had a real effect. I changed something. Now, in the absence of seeing that population and only being able to see the sample, we are very sensitive to how we sample. Because if I sampled like this, notice it doesn't look like there's any difference. And if I sampled like this, notice it looks like there's a huge difference. And so we have to use a statistical test to go beyond just computing the means, but to really try and give ourselves some confidence about whether a difference existed or not. Now, depending on how I sample, it will affect my p-values. And so I can have type 1 and type 2 errors. But my point here is to say that we do need to go beyond just eyeballing the sample data. We do need to have some more rigorous or formalized, even if it is not mathematically precise, some fashion by which to create a criteria to accept or reject our hypotheses. Let's see how we might do this. And to do that, let's talk about the difference between one-sided tests and two-sided tests. Previously, we talked about two-sided tests. We said, my guess is that this thing has changed. It's increased or it's decreased. In order to prove that, maybe that's what I want, in order to prove that, I'll create my null hypothesis, which I'll seek to reject. Well, if I want to show that I had an effect, good or bad, my null hypothesis would be there was no effect. And as a little sleight of hand, I said, well, maybe we know what the previous value is, so my null hypothesis will be the new population mean is equal to whatever the old population mean is, and I know that set value 75. And I'll look to accept that alternative hypothesis that it's not 75, it's above or below. Well, that was two-sided, and that's why when I computed that p-value, I had to multiply times 2. Let's look at a one-sided test, a one-sided z-test. Here, what I'm going to say is, that I made a change is not really what I'm looking for. What I'm looking for is I made a good change or a bad change. I increased this or I decreased this. And let's say what I want to say is, I did something that improved the situation in my data center. I decreased the temperature of the devices using some better passive cooling, distributing compute better, building the case better, whatever I happen to actually do as part of my work. If I'm looking to prove that the after population's mean is less than what it was before, and I'm fixing that before value ahead of time, I'm not going to compare the before and the after just yet, I'm just going to compare it against a fixed value. My null hypothesis would be the inverse of it. It would say, oh, well, the after population's mean is not less than, it's greater than. Instead of this being an exact equality, which has that two sides to it, this now has one side to it. And it slightly changes how I construct my z-test. Remember, I'm still working under the assumptions that I know the standard deviation of the population and that the population is normally distributed. Here, I compute my z-test using stats models, and I give it the alternative. I say, well, my alternative hypothesis is that it's smaller. If I don't give this, it assumes the alternative hypothesis is not equal, that it's two-sided. And here you can see the z-test gave me my test statistic and my p-value. My test statistic was negative 15. Well, that doesn't really mean that much unless I know what the distribution is. But when I apply that to the distribution via the CDF, it tells me that the probability, given the sampling that I'm looking at, that the actual entirety of the population afterwards got worse, higher temperature, is very small, 2 to the negative 51st. And so there is an extremely high likelihood that my change worked and my change made it better. It lowered the temperature. The way that this z-test is computed, well, you've seen this before. What we do is we take the after sample's mean, we see what its distance is from the target value, and we normalize that by the after sample standard deviation. At least that's how stats models does it. And we then just plot that on the CDF and say, what's the probability of seeing that test statistic? What is our critical region? And so you can see here our stats model z-test can tie out directly to our own formulation for the z-test. The values tie out exactly. If instead of doing this as a one-sided test, I want to do this as instead of doing this as a single value, I want to do this as a single value with a one-sided or a two-sided test. I want to look at a paired test. I want to look at the before and the after. I want to presume that I don't know the fixed value of the before or after population. I only have a sample of the two, and I want to compare the two samples. Here you can see a paired test. Or actually, here you can see a comparative test. We'll talk about paired tests in just a moment. Here, I have the before population. Here, I have the after population. And in this formulation, what I'm going to say is I'm looking for the before population to not be the same mean as the after population. I'm looking for them to be different. And if I'm looking for that, I want to set my null hypothesis to be the opposite of that. I want to prove my accept or reject my null hypothesis in order to develop confidence around that I can prove or disprove this alternative hypothesis. I'm making the same assumptions as before, that these things are normally distributed, that we know what the standard deviation of the population is, and one other assumption I'm going to make in this z-test is that the standard deviations of the two populations are the same. And I can give my z-test, my stats model z-test, two populations. And I can ask it, what's the test statistic, and what is the p-value? And you'll see most of these tests look the same. Compute a test statistic against the distribution and see what the p-value would be given that test statistic and given that distribution. And you can see very low probability that my null hypothesis is true, that the two populations have the same means. And clearly, look, just looking at the values, 176, 169, I could say that. But here I can statistically put some confidence around. I am very, very confident that it's not just a sampling issue. Remember, and I cannot stress this enough, I can change how I sample, or I could have inadvertently sampled this differently, and you can start to see some different values. Here, I have a much harder null hypothesis to reject given this particular sampling, or given this sampling, I have a very easy null hypothesis to reject. And so we are still sensitive to the sampling, but what we're trying to do is get some confidence based off of some assumption that, in general, what does a sample look? In a moment, we will talk about how we can address some of this error using approaches like bootstrapping. But for the most part, let's talk about just our z-test. How do I compute this z-test? Well, for the stats model z-test, what it's going to do is it's going to look at the difference. It's going to look at the absolute difference of the two means. And the test statistic is going to be, what is the difference in those means normalized by the two variances. At least that's what it should be if we formulated this as you typically talk about z-tests. When you look at this particular test statistic, it does not match up to what stats models give us because stats models assumes that we can pool these variances. It makes some additional assumptions in its implementation of the z-test, and what it calls a z-test isn't really what we would call, at least in a textbook, a z-test. But what stats models is doing is it's pooling these two variances. So it's computing this denominator by taking the two variances and scaling them in this particular fashion. And you can see now I've tied this out. And given this test statistic that matches up, it's still basically applying it to my normal distribution. And so when you look at trying to tie out values in tools like stats models or scikit-learn or SciPy, one of the things you should be aware of is how they're computing the test statistic and what distribution they're computing or they're comparing this against. But for the most part, really those are the two major questions for these tests. What distribution are we comparing it against? How do we compute the test statistic? And that directly gives us our p-value. Now, let us talk about what happens if we have a very small sample. And how does that affect our ability to perform these tests? If we have a very small sample, this little trick that stats models did, where it says, I can't tell you what the population standard deviation is because I don't know anything about the population, I'm only looking at the sample, but I can get close to it with my standard deviation with that Bessel's correction, that's no longer going to be that accurate because, the difference between the different possibilities for the standard deviation with a very small sample can be very large, and it can be very sensitive to how I've sampled. And so we may need a better way in which to assess this null hypothesis. Here, my null hypothesis is whether or not the sample that I'm looking at is equivalent to any other sample, which is a very good question. In addition to asking questions like, is this value close to, or given this sample, is it likely that the actual mean is this or not? And that can answer questions like, did I make things better or worse? Did I change things? Is this noise or did something happen? Instead of asking the one-sided, is the actual sample mean greater or less than a value, which can say, oh yeah, I made it better, I made it worse, these kind of questions. Instead of comparing two populations and saying, oh, the before mean and the after mean are the same, which can tell you things like, oh, your change had no real effect, at least not in the aggregate, or your change had an effect in the aggregate. Here, what I can also test is my sample representative of any arbitrary sampling of the population? And this will be my null hypothesis, that my sample is representative of any arbitrary sampling of the population. My alternative hypothesis will be, no, it's not representative. The mean of this sample is not close to the mean, and I should make sure that these are both means, of any arbitrary sampling of this. And in order to do that, what I can do is I can break apart my z-test a little bit. I can look at my standard error. That's what that denominator of that z-test was. I can look at my z-score, how far you are away from the mean, divided by that standard error. I can compute from this my p-value using a normal distribution, and from that I can determine a confidence level, a confidence interval. I have 93% confidence that this particular sample is not representative of any arbitrary sample. And this is a question that I can ask. There are many different questions that we can ask, but largely what we need to think about is, how do I relate what I'm looking to answer about the world to some summary statistic, a mean or a standard deviation? Given that and the assumptions that I can make, how do I compute a sample statistic on this that says, oh, given your data, this is how I compute that one thing, the mean, the standard deviation, whatever it is, on that particular sample, and then relate that to some rejection region or critical region, and from which to determine a p-value. If I have a p-value, I have to see what is my threshold for acceptance, and once I have all those pieces, I can say, yes, I agree. This is a representative sample. Yes, I agree. This is probably what the actual mean is. Yes, I agree. There was no perceptible difference. Yes, I agree. There was a difference and it was an increase. Yes, I agree. There was a difference and there was a decrease. Or sorry, we should say, yes, I disagree. I reject the null hypothesis in each of those cases.